Astronomers often call NGC 6872 the Condor galaxy, a fitting name for a system that spreads its wings wider than almost any other spiral known in the universe. This titanic barred spiral stretches nearly 522,000 light-years from tip to tip, more than 5 times the diameter of the Milky Way, making it one of the largest disk galaxies ever catalogued. Its elongated arms, distorted and drawn outward, form a graceful yet chaotic panorama sculpted by gravity, bearing the unmistakable signature of cosmic encounters. The colossal spiral resides about 212 million light-years away in the constellation Pavo, the Peacock. It does not exist in isolation. The smaller companion galaxy IC 4970 clings tightly to its side, having brushed against the massive disk in the past. That gravitational handshake triggered powerful tidal forces, stretching the outer arms into streams of stars and gas. Radio observations have revealed long ribbons of neutral hydrogen curling away into intergalactic space, silent testimony to the violence of their dance. Star formation ignites along the distorted arms of this galactic titan, where compressed gas clouds collapse into clusters of brilliant blue stars. Ultraviolet imaging from NASA's GALAX telescope has highlighted regions bursting with youthful stellar nurseries, some forming at distances that place them far beyond the original disk. These clumps could one day evolve into independent dwarf galaxies, born directly from the material ripped out of their parent. In this way, the Peacock spiral serves as a laboratory for understanding how galaxy interactions seed entirely new stellar systems. At its heart, the Condor giant contains a luminous barred core, a common structure in disk galaxies, but here amplified by its immense scale. Simulations suggest the bar channels gas inward, feeding central starbursts and perhaps a supermassive black hole hidden behind dust and older stars. The dynamics of such a gargantuan structure provide astronomers with valuable data on how angular momentum is redistributed in extreme environments. Would you like me to keep going and expand further, covering its discovery history, the telescopes that studied it, and its significance for theories of galactic evolution? The stellar Condor was first catalogued in the 19th century, but its true grandeur only became clear with modern imaging from observatories such as the Very Large Telescope in Chile and the Hubble Space Telescope. Each new wavelength, optical, ultraviolet, infrared, and radio, has added layers of insight. Radio maps in particular have revealed that the intergalactic behemoth is wrapped in enormous halos of hydrogen, extending even beyond its already astonishing visible disk. These halos are key to understanding how such giants accrete and redistribute matter across cosmic time. Dynamical simulations show that the cosmic Leviathan is locked in a slow, complex dance with IC 4970. The smaller companion galaxy is thought to have passed through the disk of its massive neighbor about 130 million years ago, pulling out tidal tails and warping its spiral arms. These interactions act as natural experiments in galactic physics, illustrating how gravity alone, without any physical collision of stars, can sculpt majestic new forms. Such studies also hint at the fate of our own Milky Way, which is destined to merge with Andromeda in roughly 4 billion years. The celestial predator is not merely an object of beauty but also a laboratory for studying the thresholds of starburst activity. Its outskirts host star-forming clumps tens of thousands of light-years away from the galactic center, something rare in most spirals. These distant nurseries allow astronomers to test how interstellar gas behaves when torn from its gravitational anchor and exposed to the emptier intergalactic medium. They also raise the possibility that tidal debris may serve as the birthplaces of future dwarf galaxies, altering the population of smaller systems in the surrounding cosmic environment. In addition, the barred Colossus offers clues to dark matter distribution. The way its arms extend so far without tearing apart suggests a massive, stabilizing halo of unseen matter that envelopes the system. Modeling these dynamics provides one of the few natural laboratories for estimating dark matter halos around spirals at this extreme scale. By comparing the motion of stars and gas in the wings of the galaxy with theoretical predictions, astrophysicists can refine their understanding of how dark matter sculpts the skeletons of cosmic structures. The Pavo Colossus sits in a small group rather than a rich cluster, a sweet spot where encounters are slow enough to be transformative but not so violent that the disk is shredded outright. On a prograde flyby, the companion's gravity torqued the rotating disk, launching material outward along nearly ballistic trajectories and piling gas into shocks where dust lanes now run like graphite seams along the leading edges of the bar. Those shocks compress the interstellar medium, lowering the tumor Q stability parameter below unity in patches and tipping clouds into collapse. The payoff is visible in ultraviolet, strings of luminous O and B stars tracing the arc of each tidal wing like beads on a wire, natural chronometers that let astronomers date the passage by reading age gradients from the base of the arms to their farthest curls. The wing giant also teaches the difference between ram pressure and tides. In clusters, hot intracluster gas can strip a galaxy clean. Here, with a thinner intragroup medium, the dominant sculptor is gravity itself. You can see it in the kinematics. Stars and gas share the same elongated, S-shaped streaming motions, and the rotation curve, though ragged, still climbs and then flattens, a signature of a massive, cushioning dark matter halo. Without that invisible scaffolding, the outstretched arms would tear free. With it, they flex and oscillate, storing orbital energy like springs while dynamical friction slowly saps the companion's momentum, setting the stage for a future merger. At smaller scales, the barred Leviathan behaves like a conveyor belt. Non-axisymmetric gravity torques from the bar siphon angular momentum outward, letting gas slide inward along dust lanes to the central kiloparsec, where it thickens into a pseudo-bulge and sometimes lights up in circumnuclear starbursts. In systems this large, even a modest inflow feeds thousands of solar masses of stars per year for short bursts, and if a central black hole lurks behind the glare, the same pipeline can intermittently fuel an active nucleus. The dance of inflow and feedback, radiation pressure, supernova winds, and shocks ricocheting through the bar, sets the thermostat for the next round of star formation. The Condor giant is equally valuable out in the tidal hinterlands. Gas stripped from a spiral disk is already metal-enriched, so when knots condense at the tips of the tails they can form tidal dwarf candidates with surprisingly high heavy element abundances for their small masses. That flips the usual dwarf galaxy script and gives theorists a controlled experiment. Take pre-processed disk material, expose it to low external pressure, and watch gravitational instabilities try to assemble a miniature galaxy from the top down. If those clumps survive feedback and shear, they add new satellites to the group. If not, their stars rain back, thickening the parent's outskirts. Multi-wavelength views stitch the physics together. In far infrared, the sky-raking spiral glows where dust is warmed by newborn clusters. In CO lines, observers map cold molecular reservoirs that seed those clusters, typically hugging dust lanes and bar ends where orbital resonances corral gas. HI maps reveal enormous fountains of neutral hydrogen fanning beyond the optical disk, some parcels moving fast enough to skim the edge of escape before being reeled back by the halo. X-ray points trace high-mass X-ray binaries, fresh stellar remnants that act like neon signs for recent star formation, while a faint, hotter component hints at shocks and superbubbles where clustered supernovae punch chimneys through the disk. Dynamically, the peacock spiral is a case study in resonance structure writ large. The bar's pattern speed defines corotation and inner/outer Lindblad resonances. Gas piles at the bar ends into bright ANSI, feeds an inner ring near the inner resonance, and sketches a sprawling outer ring or suturing where the spiral meets corotation. Because the disk is so extended, even small shifts in pattern speed can move these resonances by tens of kiloparsecs, rearranging where stars are born and where they migrate. Over hundreds of millions of years, resonance scattering and tidal heating puff the disk, thicken the stellar layer, and redistribute angular momentum until the system either relaxes or merges. The galactic titan also pushes on galaxy scaling laws. Interactions can knock a rotating disk off the canonical Tully-Fisher relation, making it appear overluminous for its measured velocity width or vice versa depending on where and how the width is sampled. By measuring rotation along multiple position angles and combining stellar with gas tracers, astronomers reconstruct the pre-encounter mass distribution, then watch in real time as torques move it around. That forensic approach, comparing simulations to velocity fields and cluster ages, yields a remarkably tight timeline for the flyby and a prediction for the next close pass. Seen in a cosmological context, the intergalactic behemoth is a local echo of an era when such encounters were common. At cosmic noon, around redshift 2, giant gas-rich disks collided frequently, driving spectacular starbursts and fast black hole growth. Today, the universe is more settled, so a present-day system wearing wings 500,000 light-years across becomes a Rosetta Stone. It condenses the messy, many-scale physics of hierarchical growth into a single, high-contrast frame. Read the arms and you read gravity. Read the dust lanes and you read shocks. Read the clusters and you read the clock. Ultimately, the fate of the stellar Condor is to change. If the companion is captured, the pair will spiral together, the bar will strengthen and then buckle, gas will funnel inward, and the disk could fade into an earlier type remnant with a thicker body and a quieter star-forming life. If the partner escapes after trading momentum, the wings will relax over a few rotation periods, the outer clumps will either disperse or survive as satellites, and the vast disk will keep turning, scarred but coherent, its dark halo still holding the stage. Either way, the snapshot we see now, those sweeping arms, that iron-bright bar, the blue starry embroidery, catches a giant in mid-sentence, speaking the common language of gravity in an accent all its own. Beyond its photogenic arms, the wingspan spiral encodes a clean lesson in disk stability. Where shear is strong and the epicyclic frequency is high, the Tumor Q parameter rises and star formation stalls. Where the tidal shocks from the flyby lower Q below unity, giant molecular complexes assemble rapidly, fragmenting into clusters whose mass function follows an almost universal power law. In the avian megaspiral, those triggering zones line up along the leading edges of the bar and along the most strongly curved segments of each tidal extension, letting observers read the gravitational history straight from the spatial pattern of cluster ages. Radial mixing driven by corotation scattering and transient spirals then blurs metallicity gradients, so spectroscopy across the feathered disk doubles as a chronicle of how far stars have migrated since the encounter. Gas physics in the halo-cradled Titan is equally instructive. Cold HI drapes far past the optical body, while CO traces denser pockets that only appear once midplane pressure crosses a threshold set by the local gravity of stars plus dark matter. That threshold is met naturally at bar ends and in compressed dust lanes, explaining why the bar engine giant lights up in patchy star formation rather than a continuous ring. Feedback from massive stars, ionizing radiation, winds, and clustered supernovae, carves low-density chimneys through which hot gas vents, but in a potential well this deep much of that material rains back, a galactic fountain that recycles metals and sustains a moderate, extended star-forming phase rather than a brief, catastrophic blowout. Kinematics of the bird-like colossus reveal how far gravity alone can sculpt order from disturbance. Long slit and integral field maps show S-shaped isovelocity contours, clear signatures of streaming along a non-axisymmetric potential. Pattern speed estimates, whether via Tremaine, Weinberg integrals where continuity holds or through resonance mapping with rings and bar ends, place corotation just beyond the bar tips, a configuration that optimizes gas inflow without instantly shredding the disk. Because the system is so overscaled, even a small change in pattern speed shifts resonances by tens of kiloparsecs, moving the preferred birthplaces of stars like a vast, slow-turning kaleidoscope. Environment matters, and the Pavo superdisk occupies a Goldilocks niche. The intragroup medium is dilute enough that ram pressure stripping is secondary, yet present enough that a supersonic passage can leave a narrow, low-surface brightness wake in soft X-rays, gravitational focusing writ in plasma. Nearby group members act as perturbers that will torque the ultra-extended spiral again and again across a gigayear, each pass adding or subtracting just a little angular momentum. Cumulatively, those taps can thicken the stellar layer, heat the disk radially, and slowly nudge the system toward a more spheroidal future even if the current companion ultimately escapes. Star clusters in the winged laboratory serve as clocks and thermometers. Color magnitude diagrams of the brightest associations yield ages from a few to a few tens of millions of years in the outer plumes, with internal spreads reflecting the passage of the density wave. H2 region line ratios provide gas metallicities that are surprisingly high for such remote star-forming pockets, exactly what you expect when the raw material originated inside a mature spiral disk. Those abundances, combined with dynamical self-binding tests, separate mere star-forming knots from genuine tidal dwarf candidates, letting the sky-wide behemoth test models of dwarf galaxy formation without invoking early universe conditions. Magnetic fields give another layer of order to the giant winged disk. Polarized radio continuum tends to align along dust lanes and the concave sides of arms where shear is strongest, a sign that compression and differential rotation are organizing the large-scale field. That alignment can both guide and resist gas flows. Aligned fields help channel matter along lanes into the bar, while strong magnetic tension can slow fragmentation in the outermost plumes, subtly modulating the local star formation efficiency. Cosmic ray electrons, accelerated in supernova remnants tied to the freshest clusters, backlight these structures and turn the barred megaspiral into a natural plasma physics exhibit on galactic scales. Dark matter's imprint is everywhere in the halo-dominated Leviathan. The far-flung arms maintain coherence only because an extended, massive halo keeps orbital frequencies gently varying with radius, preventing catastrophic phase mixing. Rotation curves that flatten well beyond the bright disk imply mass-to-light ratios rising outward, and when modelers fit both stellar and gas kinematics simultaneously, they recover halos that are rounder than the distorted light would suggest. That contrast, luminous chaos inside, gravitational calm outside, explains how the wingspan behemoth can look torn and yet remain dynamically resilient. Even dust in the feather-swept colossus carries memory. Mid-infrared colors separate warmth from very small grains and PAH features excited by ultraviolet photons. Where the PAH emission is suppressed, hard radiation fields or shocks likely dominate, marking recent passages of strong compressive fronts. Far-infrared SEDs track the dust-to-gas ratio and, through that, the metal yield that the Peacock giant has managed to lock into solids. Combined with stellar population synthesis, these diagnostics close the baryon budget. How much gas has turned into stars since the flyby, how much lingers cold and quiescent, and how much circulates hot in the halo. Looking ahead, the bar-forged Titan will continue to evolve on multiple clocks. On tens of millions of years, cluster populations age and fade, revealing underlying redder disks. On hundreds of millions, the bar can strengthen, then buckle and build a box/peanut-shaped bulge. On a gigayear, dynamical friction may return the companion for a second, deeper encounter. Each step will rewrite resonances, move rings, relocate star-forming arcs, and alter the system's slot on scaling relations like Tully, Fisher and the star-forming main sequence. The present snapshot of the winged superspiral is thus not a final form but a frame in a very slow movie, where gravity is the director and gas physics the script doctor. Set in a broader cosmological story, the Pavo behemoth is a low-redshift echo of gas-rich giants at cosmic noon, yet it lives close enough for us to resolve its weather. That combination, vast scale, nearby distance, and an ongoing interaction, turns the avian Leviathan into a rare benchmark for simulations that attempt to span from kiloparsec scale bars to 100 kiloparsec tidal plumes in one consistent run. When the models get the pitch angles, age gradients, and velocity wiggles right all at once, we learn not only why this single-winged disk looks the way it does, but also how countless less dramatic systems quietly rearrange themselves under the same, simple law: gravity pulling, gas yielding, stars recording. In the Raptor spiral, even the star formation law gets stress-tested at extreme radii. Where the gas surface density dips below the classic Kennicutt-Schmidt threshold, the tidal field and local turbulence still manage to assemble hinge clumps at the bends of the arms, places where shear briefly eases and shocks converge. These outsized nurseries host clusters with massive stars whose lifetimes are short enough to timestamp the passage of the perturbation, turning the outskirts of the avian superdisk into a stopwatch for the interaction itself. Cluster demographics in the wing-breadth megaspiral reveal a second clock, disruption. Tidal forces and internal two-body relaxation erode the low-mass end of the cluster mass function, so the surviving populations skew heavier with age. By comparing cluster ages and masses from ultraviolet, optical colors to models of tidal heating, astronomers back out how strongly the disk has been stirred since the flyby, a dynamical archaeology project written in blue and red. Kinematically, the barred supergiant shows textbook lopsidedness, a measurable m=1 asymmetry in both starlight and HI line profiles. That off-centeredness is common in post-encounter disks and is a sensitive probe of the underlying potential. If the dark halo is even mildly triaxial, the precession of the distorted disk can be sustained for hundreds of millions of years. Pair that with integral field velocity maps and you can disentangle which twists come from the luminous bar and which are imposed by the halo shape cradling the feathered colossus. Cold gas supply keeps the story going in the Pavo Raptor. Not all of the material torn outward is lost, a fraction follows loosely bound orbits that rain back as extended, warp streamers, thickening the outer disk and feeding future star formation. Where those returning flows intersect the rotating plane at an angle, you see corrugations, vertical ripples that gradually damp but leave behind a warmer, thicker layer, a proto-thick disk grown not by mergers alone but by the disk's own tidal weather. At the center of the winged ultraspiral, the bar's inflow occasionally piles gas into a circumnuclear ring, a resonance-caught reservoir that flickers between quiescence and bursts of activity. If a supermassive black hole sits behind the dust, its fueling is likely intermittent, brief, sub-Eddington episodes punctuating long quiet spells, the galactic equivalent of sipping rather than gulping. Outward propagating feedback from those bursts, radiation pressure and supernova-driven shocks, can momentarily raise the tumor Q in the inner kiloparsec, pausing the very inflow that fed them, a self-regulating heartbeat at the core of the Condor scale disk. Dust physics adds fine print to the tale. In the sky-wide spiral, mid-IR diagnostics show PAH features dimming where shocks and hard UV fields dominate, while far-IR colors trace cooler, more quiescent lanes at bar ends and along the concave sides of arms. That contrast maps where energy is being injected into the interstellar medium, and when combined with CO and HI data, it lays out a full supply chain from atomic gas to molecular clouds to newborn stars across nearly 500,000 light-years. Even the cosmic rays threading the giant avian disk do useful work as messengers. Polarized radio continuum sketches magnetic fields stretched by shear and compressed by shocks, revealing channels that both guide gas toward the bar and restrain fragmentation in the far plumes. Those same relativistic electrons, accelerated in supernova remnants, trace where the most recent clusters live, providing an almost real-time overlay on top of the slower evolving stellar light. On longer timescales, secular evolution will rewrite the silhouette of the peacock behemoth. Bars tend to slow as they transfer angular momentum to the outer disk and halo, corrotation drifts outward, resonance rings migrate, and the bar may eventually buckle into a box/peanut bulge. If the companion returns for a deeper pass, inflows surge, the wings may reflare, and the system edges toward an earlier type remnant. If not, the arms relax, tidal dwarf candidates either detach as satellites or dissolve, and the wingspan titan coasts into a broad, mature spiral with scars you can still read in low surface brightness light. Placed against the backdrop of hierarchical growth, the interacting megadisk is a rare nearby stand-in for the gas-rich giants of cosmic noon, but one we can resolve star-forming clump by clump. That duality, ancient process, modern clarity, makes it a calibration point for simulations striving to span from parsec-scale cloud physics to 100 kiloparsec tides in one consistent run. When those models reproduce the pitch angles, age gradients, magnetic alignments, and velocity wiggles all at once, they are not merely explaining one spectacular condor wing galaxy, they are validating the grammar by which gravity, gas, and time compose disks across the universe. The intergalactic rock also clarifies how disks redistribute metals after a tidal shock. Spectroscopy across its sprawling wings shows flattened abundance gradients compared to quieter spirals, evidence that radial mixing has ferried enriched gas far from the bar while inflows concentrate slightly more metal-rich material toward the center. That two-way conveyor, out along the arms through resonance scattering and back down the bar via torques, turns the winged superdisk into a chemical blender, erasing the sharp metallicity steps that would otherwise trace a galaxy's inside-out growth. Stellar migration leaves kinematic fingerprints in the Pavo Titan. Beyond simple heating, stars caught near corrotation can trade angular momentum with transient spirals and the bar, changing radius without gaining much random motion. The result is a surprisingly cool, extended population in the outskirts that still carries the thin disk's ordered rotation. When modelers match these cold tails and the S-shaped isovelocity contours simultaneously, they constrain the depth and shape of the dark halo cradling the feathered leviathan, because only certain halo profiles prevent the arms from phase mixing away. Viewed in ultraviolet, the bar-wrought giant behaves like an extreme X-UV disk. Clusters flare at arm bends and tail tips where shocks and lower shear briefly coexist. In infrared, dust heated by those clusters picks out the gas supply chain, atomic reservoirs in the far plumes, molecular pockets where pressure climbs near bar ends, and warm dust crescents hugging the leading dust lanes. Radiopolarization adds the magnetic overlay, showing fields stretched along concave arm edges and funneled into the bar, a topology that both guides inflow and gently resists fragmentation in the most rarefied wings of the raptor spiral. Environment frames the long game for the ultra-extended spiral. In a modest group, repeated, slow perturbations are more likely than one violent cluster encounter. Each pass from neighbors tweaks the pattern speed, nudges resonance rings, and restirs the outskirts. Over a gigayear, such harassment light can thicken the disk and fuel episodic central starbursts without ever fully destroying the grand design structure. If the current companion returns on a tighter orbit, the bar should strengthen, then buckle into a box/peanut bulge, a secular metamorphosis many barred disks undergo but here writ across a canvas hundreds of thousands of light-years wide. Even without a blazing nucleus, the Condor scale disk offers an AGN testbed. Intermittent gas delivery to the inner kiloparsec, punctuated by feedback that raises the local tumor Q, naturally produces flickering low-luminosity activity rather than continuous feeding. Shock-excited line ratios in circumnuclear gas and the statistics of high-mass X-ray binaries around the core help separate quiet black hole sipping from pure starburst heating, letting observers time the heartbeat of the sky-wide spiral without a quasar's glare. Comparisons sharpen its uniqueness. Malin-class giants achieve vast size with diffuse, low-surface brightness disks. UGC 2885 packs mass into a relatively quiescent, symmetric behemoth. By contrast, this avian megaspiral couples extreme scale to clearly tidally sculpted structure, flared wings, offset light, patchy outer star formation, and a bar that still manages to regulate the core. That combination compresses multiple chapters of disk evolution, interaction, migration, bar fueling, feedback, into one readable system. Cosmologically, the interacting megadisk plays translator between epochs. At redshift 2, gas-rich giants collided frequently. Today, such dramas are rarer and calmer. Because the Peacock Colossus lives near enough for clump-by-clump resolution, simulators can ask their models to hit all the notes at once: pitch angles, age gradients, magnetic alignments, velocity wiggles, metallicity maps. When a single run reproduces those observables together, confidence grows that the same physics governs less spectacular disks that evolve off-camera throughout the nearby universe. Even the faintest structures add lines to the story. Low surface brightness imaging around the wingspan Titan reveals stellar streams and shell-like debris that likely predate the current flyby, a palimpsest of earlier encounters. Those fossils show that what looks like a one-off spectacle is more often a chapter in a serial, angular momentum traded, orbits reshaped, outskirts thickened, satellites spawned and sometimes reaccreted, gravity's patient editing on a page the size of 500,000 light-years. Projecting forward, the barred supergiant faces a branching script. Capture the companion, and the pair spiral together, gas floods inward, the bar strengthens, buckles, and builds a thicker body. Tidal dwarfs either survive as satellites or fall back to puff the halo, the remnant drifts toward an earlier type. Miss the capture, and the wings gradually relax over a few rotation periods, streams rain back, the center keeps its self-regulated pulse, the outer disk stays laced with star-forming knots whenever returning gas intersects the plane. In both versions, the galactic Condor remains a masterclass in how gravity sculpts, gas negotiates, and stars keep the minutes. The feathered superspiral even lets us test how orbital families inside a bar choreograph gas. Along X1 orbits aligned with the bar, clouds pile into straight dust lanes that act like shock fronts, where the potential admits X2 orbits perpendicular to the bar. Inside the inner Lindblad resonance, inflowing material can stall into a circumnuclear ring and light up in H2 knots. Phase offsets between the stellar bar and the gaseous lanes measure the torque directly. Gas leads where it loses angular momentum and trails where feedback has briefly raised stability. Stitching these azimuthal phase shifts around the Condor scale disk yields a torque map, the closest thing astronomers have to seeing gravity push on gas in real time. Out along the tidal wings, the Pavo megaspiral displays the classic, beads-on-a-string, morphology, nearly periodic spacing of star-forming clumps along a filament, a hallmark of gravitational fragmentation moderated by shear and magnetic tension. The clumps grow where the effective sound speed, including turbulence and field support, drops, then they self-regulate via winds and radiation pressure from massive stars. The ratio of H-alpha to far ultraviolet light varies systematically from the base of each plume to its tip, a built-in age gradient that timestamps the passage of the density wave and lets the wingspan colossus double as a chronograph for its own encounter history. Globular cluster archaeology adds another layer. Young massive clusters forming in the compressed bar ends and in hinge clumps may be the immediate cousins of long-lived globulars if they can survive early mass loss. Their initial mass function, internal density, and ambient tidal field decide that fate. By comparing cluster catalogs across the avian superdisk with dynamical models of evaporation and tidal shocking, observers can predict which newborns will endure for billions of years and which will dissolve into the smooth background, subtly reddening the outer arms. The circumgalactic medium of the halo-cradled giant matters as much as the bright disk. Neutral hydrogen streams arc beyond the optical light, while hotter, X-ray emitting gas hints at shocks where returning material plunges back through the plane. Metals carried outward by fountains and tidal outflows seed this halo, so when gas rains back it is already enriched, flattening abundance gradients that would otherwise steepen with radius. That metallic echo is the chemical memory of past starbursts, written in diffuse light tens of kiloparsecs from the core. On the dark matter stage, the bar-forged titan constrains halo shape. If the halo were too cuspy and prolate, the elongated arms would precess rapidly and smear out. If too chord and oblate, the bar would slow excessively and overfeed the center. Velocity fields that keep their S-shaped twist across huge radii imply a fairly round, extended halo whose circular velocity changes gently with distance, exactly the scaffold needed to hold 500,000 light-year wings together without tearing them free. Subtle warps and lopsidedness, m=1 modes, persisting for hundreds of millions of years further suggest a halo that is not perfectly spherical, allowing the peacock behemoth to maintain its off-center light while still rotating coherently. Even dust in the sky-wide spiral encodes dynamical weather. Mid-infrared spectra show where PAH carriers are shattered by shocks, mapping recent compressive fronts. Far-infrared spectral slopes trace cooler, quiescent sectors at bar ends where gas lingers near resonances. Combine those with CO maps of molecular reservoirs and you reconstruct a supply chain from atomic gas in the plumes to cold clouds at the bar ends to hot, feedback pressurized cavities near young clusters, a complete life cycle of interstellar matter paced by the bar's pattern speed. Projecting forward, the Raptor disk will keep editing itself. Bars tend to slow as they torque the outer disk and halo, corotation drifts outward, resonance rings migrate, and the bar may eventually buckle, building a box/peanut bulge. A renewed close pass by the companion would reflare the wings and spike central inflow. A long separation would let the plumes relax while returning streams thicken the outskirts and seed more low-level star formation. Either branch preserves the lesson this galactic condor already teaches so cleanly: gravity sculpts the stage, gas negotiates the terms, and stars take notes, leaving a readable record from the circumnuclear ring to the farthest, faintest curl of each tidal feather. Seen through the lens of orbital dynamics, the winged superdisk is a living demonstration of swing amplification at work, modest, m=2 perturbations sheared by differential rotation balloon into grand, long-pitch spirals when the disk's self-gravity, shear, and epicyclic frequency fall into the right ratios, and the companion's tidal tug simply seeds the pattern that the disk then overamplifies. Where the shear parameter is lower at large radii, the pitch angles open, explaining why the outer wings of the Pavo megaspiral remain broad and feathery while the inner arms hug the bar more tightly. Power spectra of starlight and gas emission in such systems typically show a turbulent cascade with slopes near Kolmogorov values, implying that energy injected by feedback and tides percolates across scales, from clustered supernovae carving kiloparsec superbubbles to cloud-scale shocks that set the sonic Mach number and, ultimately, the star formation efficiency. Even vertical structure in the feathered colossus carries the imprint of the flyby. Bending waves ripple through the outer disk after an encounter, leaving corrugations that damp only slowly in a massive halo. Their phase with radius tells you how the perturbation propagated, while their amplitude brackets the ratio of disk to halo mass. Combined with the observed warp of the far HI layers, these waves argue for a deep, gently rising rotation curve that cushions the outstretched arms against rapid phase mixing. In that same halo, returning tidal streams intersect the plane at angles that thicken the outskirts and seed fresh, low-level star formation long after the main shock has passed, so the Condor scale disk writes its own epilogue in faint UV knots beyond the classic optical edge. Chemistry adds timestamps. Flattened radial metallicity gradients betray the two-way traffic of metals. Fountains and tails export enriched gas outward while bar-driven inflow concentrates slightly more metal-rich material near the center. H2 region diagnostics in the plumes show near-solar abundances despite their distance, exactly what you expect if those nurseries condensed from pre-processed disk gas rather than pristine inflow. Cluster luminosity functions skew bright at hinge clumps where compression is strongest, and their age spreads, often a few to a few tens of mere, act like contour lines on a time map of the avian leviathan's recent past. Magnetism and cosmic rays outline the hidden scaffolding. Polarized radio continuum typically aligns along concave arm edges and bar dust lanes, signaling fields stretched by shear and compressed by shocks. Those fields both guide gas toward the inner kiloparsec and add magnetic pressure that slightly raises the effective gene's length in the far plumes, modulating fragmentation. Relativistic electrons backlight this geometry, tracing the freshest clusters where supernovae have already begun to accelerate particles, so the Peacock giant doubles as a natural laboratory for galactic-scale plasma physics. At the core, orbit families control the pacing. Gas on X1 orbit streams along the stellar bar into offset dust lanes, shocks, cools, and, if inner Lindblad resonances permit X2 orbits, stalls into a circumnuclear ring where star formation pulses in bursts. Feedback from those bursts temporarily raises the tumor Q, throttling inflow until turbulence decays. If a central black hole lurks, it will be fed intermittently, producing flickering, low-luminosity activity rather than steady accretion. Over hundreds of millions of years the bar in the Raptor spiral will likely slow and strengthen, then buckle into a box/peanut bulge, migrating corotation and outer resonances outward and rearranging where rings, spirals, and star-forming crescents prefer to live. Set against other giants, the galactic Condor fills a rare niche. Unlike ultradiffuse Malin-class disks or the massive yet orderly UGC 2885, this system weds extreme size to clear tidal sculpting, letting theorists test in one frame how non-axisymmetric torques, dark matter halo shape, turbulence, magnetic fields, and feedback conspire to build and remodel a spiral on 500,000 light-year scales. Read the pitch angles and you measure shear. Read the age gradients and you recover the encounter clock, read the velocity wiggles and you weigh the halo. In that sense the wingspan Titan is both spectacle and standard, a single, nearby benchmark that encodes the grammar by which gravity writes, gas edits, and stars archive the evolving story of a giant disk. High-resolution kinematics turn the Condor scale disk into a workbook for multi-component stability. When you combine stars and gas, the effective Q is not a single number but a weighted blend, with a thickness correction, that varies around the bar and along each plume, where Q** is high but Q_gas is low, compression still wins and cloud complexes assemble, while where both are high the arms look dust-rich yet quiescent. Fourier decompositions of the light and velocity fields show strong m equals 2 power from the bar plus a persistent m equals 1 lopsidedness, and the swing amplification parameter x hovers in the sweet spot that lets modest seeds balloon into grand, open spirals. In that regime the avian megaspiral amplifies what the encounter begins, so the morphology is a dialogue between external tides and the disk's own self-gravity. Age dating across the wingspan colossus works like dendrochronology for galaxies. H-alpha isolates the last 10 µm of activity, far UV stretches the baseline to 100 µm, and optical colors reach deeper, so stacking these tracers along a tail reveals a clean age gradient, youngest at the compressed bends, older toward the base. Where clumps sit near local shear minima, hinge points at curvature changes, they grow massive, young clusters with shallow luminosity functions. Some will dissolve under tidal stress and two-body relaxation, others, born dense, may survive to become ancient globulars. Thus the peacock behemoth is simultaneously growing ephemeral blue lace and seeding its red, long-lived jewelry. The bar inside the raptor spiral writes its own resonance script. Corotation just beyond the bar tips marks a fast bar, inflow streams along offset dust lanes, shocks, and either plunges inward or stalls into a circumnuclear ring if inner Lindblad resonances support X2 orbits. Feedback from clustered supernovae then raises turbulence and the local Q, briefly throttling the same inflow that fed the burst, a self-regulating loop. Over hundreds of millions of years, torques to the outer disk and halo slow the pattern speed, migrating corotation outward, shifting ring radii, and setting up the bar to buckle into a box/peanut bulge. The bar-forged titan is therefore not static architecture but a machine that edits its own blueprint. Chemistry and dust in the sky-wide spiral trace the supply chain. Metallicity gradients flatten after the flyby as enriched gas rides tails outward while bar torques pull slightly more metal-rich material inward. Mid-IR spectra dim in PAH features where shocks and hard UV fields dominate, tagging fresh compressive fronts, far IR colors cool at bar ends and on concave arm faces where gas lingers. Combine those with HI maps of atomic reservoirs and CO maps of molecular pockets and you can follow atoms from diffuse halos into clouds, into clusters, and back to halos via fountains, a full baryon life cycle unfolding across 500,000 light-years. Magnetic fields and cosmic rays give the feathered Leviathan its invisible filigree. Polarized radio continuum aligns along concave arm edges and bar lanes, showing fields stretched by shear and compressed by shocks. Magnetic pressure slightly raises the effective gene's length in the far plumes, modulating fragmentation. Relativistic electrons from recent supernovae backlight this geometry, so radio maps overlay a near real-time record of where the most recent clusters exploded. The result is a plasma physics laboratory at galactic scale, where turbulence, shear, and field topology co-govern how gas becomes stars. Even the vertical structure of the ultra-extended spiral records the encounter. Bending waves, corrugations in the outer disk, propagate and damp slowly in a deep, nearly round halo, their amplitude with radius brackets the disk-to-halo mass ratio. Warped HI layers and returning tidal streams intersect the plane at angles, thickening the outskirts and lighting faint UV knots beyond the canonical optical edge. Long after the main tug has passed, the interacting megadisk keeps writing a quiet epilogue in low surface brightness ink. Placed among peers, this galactic condor fills a rare niche. Malin-class giants reach vast size with ultra-diffuse symmetry. UGC 2885 is massive yet orderly. Here, extreme scale couples to unmistakable tidal sculpting, flared wings, off-center light, patchy outer star formation, and a bar that still regulates the core. That compression of phenomena, interaction, migration, bar fueling, feedback, into a single nearby system turns the winged superspiral into a benchmark. Match its pitch angles, age gradients, metallicity maps, polarization patterns, and S-shaped velocity contours all at once, and a simulation has earned the right to generalize. Projecting forward, the Pavo colossus follows a branching future. If the companion is captured, dynamical friction will draw it inward, inflow will surge, the bar will strengthen and buckle, the disk will thicken and drift toward an earlier type remnant while any tidal dwarf candidates either survive as satellites or fall back to puff the halo. If the partner escapes after trading momentum, the wings will relax over a few rotation periods, streams will rein back, the center will keep its self-regulated heartbeat, the outskirts will remain speckled with star-forming knots wherever returning gas intersects the plane. Either way, the lesson stands. Gravity sculpts, gas negotiates, stars take notes, and the condor-winged giant preserves the minutes from nucleus to farthest feather. Deep imaging shows the wingspan colossus breaks the tidy exponential that textbooks love. Its surface brightness profile upbends in the outskirts, a Type 3 disk grown by tidal stirring and reaccretion, while color maps fade more gently than in calm spirals because radial mixing and metal-enriched fallback have blurred the usual gradient. Spectroscopy along the bar and into the plumes finds ionized gas line ratios consistent with shock plus photoionization hybrids, the fingerprint of gas compressed in lanes and then lit by clusters born minutes ago on a galactic clock. Where shear is lowest at curvature changes, hinge clumps appear with nearly periodic spacing, a beads-on-a-string morphology set by the effective gene's length once turbulence and magnetic tension are counted. Kinematics of the Pavo megaspiral underline that order can survive violence. Tilted ring fits to HI and harmonic decompositions of ionized gas reveal coherent rotation with strong non-circular streaming along the bar. S-shaped isovelocity contours testify to a non-axisymmetric potential whose pattern speed places corotation just outside the bar tips, a fast bar configuration that maximizes inflow without shredding the disk. The swing amplification parameter hovers in the sweet spot, so modest m equals 2 seeds planted by the flyby bloom into long-pitch spirals, while a persistent m equals 1 lopsidedness advertises the off-center mass distribution and a halo that's extended and fairly round rather than razor-cuspy. Star formation in the Raptor disk is patchy by design. The classic Kennicutt-Schmidt trend bends in the far wings, surface densities are low, yet compression at bends and bar ends pushes gas above the midplane pressure threshold for the atomic-to-molecular transition. Cold CO pockets thus appear right where dust lanes meet resonances, and far IR dust crescents warm under newborn clusters. Depletion times stretch long in the plumes, but the clusters that do form are clean chronometers, H-alpha catching the last 10 mir, FUV the last 100 mir, so age gradients from tail base to tip timestamp the encounter as neatly as tree rings. Chemistry in the feathered giant reads like a stirred pot. Abundance gradients flatten after a tidal shock because metals ride outward in tails while bar torques pull slightly richer gas inward, fountains and reaccretion then seed the circumgalactic medium with enriched material that returns already preprocessed. Tidal dwarf candidates at tail tips inherit these high metallicities relative to their masses, a telltale that they condensed from disk debris rather than dark matter-dominated mini-halos. Kinematic tests, velocity dispersion versus luminosity, separate bound dwarfs from ephemeral star-forming knots and, in either case, record where disk material briefly tried to become its own galaxy. The bar of the Condor scale spiral is a machine that edits its own blueprint. Gas on X1 orbit streams into offset shock lanes. If inner Lindblad resonances admit X2 orbits, a circumnuclear ring traps inflow and lights in bursts. Feedback raises turbulence and the local tumor Q, throttling the inflow that fed the burst, a self-regulating heartbeat. Over a few hundred mir, torques send angular momentum to the outer disk and halo, slowing the pattern and nudging corotation outward. The bar then thickens and can buckle into a box/peanut bulge, subtly changing where rings stall and where spirals launch. Magnetism threads the sky-wide spiral with invisible rails. Polarized radio continuum aligns along concave arm edges and bar lanes, mapping fields stretched by shear and compressed by shocks. Magnetic pressure modestly raises the effective gene's length in the thinnest plumes, tempering fragmentation. Cosmic ray electrons from fresh supernovae backlight the pattern, turning the system into a natural plasma physics lab where turbulence, shear, and field topology jointly regulate how clouds collapse and when they don't. Vertical structure in the ultra-extended disk keeps score of the flyby long after the headline act. Bending waves ripple through the outskirts and damp only slowly in a deep, nearly round halo. Warped HI layers and returning streams cross the plane at angles, puffing a proto-thick disk and planting faint UV knots beyond the classic optical edge. Those ripples bracket the disk-to-halo mass ratio and, together with the survival of the 500,000 light-year wings, argue for a gently rising rotation curve that cushions the outstretched arms against rapid phase mixing. Compared with other giants, the peacock behemoth compresses many chapters of disk evolution into one frame: interaction-seeded spirals, bar-driven inflow, feedback-regulated bursts, metal mixing, magnetic guidance, reaccretion-grown outskirts. The same diagnostics that make it spectacular also make it standardizable. Match its pitch angles, torque phase shifts, age gradients, metallicity maps, polarization patterns, and S-twisted velocity fields simultaneously, and a simulation has earned the right to generalize, because the galactic condor is not just a showpiece, it is a rubric for how gravity writes, gas edits, and stars archive the long, legible sentence of a giant spiral galaxy. The Raptor disk also lets astronomers test which star formation law actually rules the outskirts. In low-density wings where the classic surface density threshold would predict little activity, a pressure-based recipe tied to mid-plane gravity does better. Once dust lanes at bar ends or arm bends lift the mid-plane pressure above a critical value, Hi converts to H2 and clusters ignite even at galactocentric radii that would be quiescent in calmer spirals. That switch is visible when CO appears exactly where dust lanes intersect resonances, and it explains why the winged megaspiral looks stitched with patchy star-forming crescents rather than a continuous ring. Depletion times stretch long in the plumes, gas lingers for hundreds of mere, but the few massive, hinge clumps that do form are clean clocks, their H-alpha and FUV ratios timestamping the shock's passage with mere precision. Kinematically, the Pavo superdisk separates ordered rotation from true radial flow using harmonic decomposition of velocity fields, and m equals 2 term tags bar streaming, m equals 1 lopsidedness announces the off-center mass distribution, and higher modes isolate localized shocks. Where radial components peak, dust lanes sharpen and CO brightens, confirming that non-axisymmetric torques are actually moving gas, not just stirring it. Pattern speed estimates, Tremaine, Weinberg from the old stellar light, resonance mapping from rings and arm turnovers, consistently place corotation just beyond the bar tips, a fast bar state that maximizes inflow without destroying the disk, a remarkable balance for a system as outsized as the Condor scale spiral. Chemically, the feathered colossus behaves like a well-stirred mixer. Oxygen abundance gradients flatten after the flyby because metals ride outward in tails while bar inflow pulls slightly richer gas toward the center. Fountains and reaccretion then seed the circumgalactic medium with enriched material that later rains back already preprocessed. Tidal dwarf candidates at tail tips inherit high metallicities for their masses, exactly what you expect if they condensed from disk debris rather than pristine mini-halos. Kinematic self-binding tests, velocity dispersion versus size and luminosity, separate real dwarfs from ephemeral knots, so the sky-wide spiral can literally be seen experimenting with dwarf galaxy formation in situ. The bar inside the avian leviathan edits its own blueprint through secular evolution. Angular momentum transfer to the outer disk and halo slows the pattern speed over hundreds of mere, migrating corotation outward and shifting ring radii. Once enough vertical heating accumulates, the bar buckles, building a box/peanut-shaped bulge. Inflow fed by straight dust lanes then cycles between bursts and lulls as feedback spikes the local tumor Q, briefly throttling the very pipeline that fueled the burst. If a central black hole hides behind dust, its diet will be intermittent, sub-Eddington sips rather than continuous accretion, so the peacock giant tests duty cycles for quiet AGN without the glare of a quasar. Magnetic structure gives the wingspan titan its invisible rails. Polarized radio emission lines up along concave arm edges and bar lanes, showing field stretched by shear and compressed by shocks. That ordering adds magnetic pressure, raising the effective gene's length in the thinnest plumes and subtly suppressing overfragmentation. At the same time, field-guided flows help channel gas into the bar. Cosmic ray electrons from fresh supernovae backlight this geometry, turning the outer plumes of the Raptor galaxy into a plasma physics testbed where turbulence, shear, and field topology co-govern how clouds collapse. Vertical structure records the encounter in low-contrast ink. Bending waves ripple through the outskirts of the ultra-extended spiral, damping only slowly in a deep, nearly round halo. Warped HI layers and returning tidal streams cross the plane at angles, thickening the outer disk and planting faint UV knots beyond the classic optical edge. The amplitude and phase of those corrugations bracket the disk-to-halo mass ratio, and together with the survival of 500,000 light-year wings, they argue for a gently rising rotation curve that cushions the outstretched arms against rapid phase mixing. Comparative anatomy clarifies why this galactic condor matters. Malin-class giants reach vast size with ultra-diffuse, largely symmetric disks. UGC 2885 is massive yet orderly. Here, extreme scale couples to unmistakable tidal sculpting, flared wings, offset light, patchy outer star formation, and a bar that still regulates the core. Because the system sits in a modest group rather than a crushing cluster, gravity, not ram pressure, does most of the sculpting, letting theorists isolate tidal physics from hydrodynamic stripping. That makes the Pavo megaspiral a clean benchmark for simulations that must span from parsec-scale cloud formation to 100 kiloparsec tides in one consistent run. Even the faintest structures add lines to the narrative. Deep, low surface brightness imaging around the interacting megadisk reveals earlier shells and streams, fossils of past minor encounters that predate the current flyby. Stack those with the present wings, and you see a serial editor at work, angular momentum traded over and over, orbits reshaped, outskirts puffed, satellites spawned and sometimes reaccreted. Forward models then branch, capture the companion, and inflow surges, the bar strengthens and buckles, and the remnant drifts earlier type, miss the capture, and the wings relax over a few rotation periods while returning gas keeps the outskirts speckled with slow, low-efficiency star formation. In both endings the Condor galaxy remains legible, gravity sculpts, gas negotiates, stars take notes, and the record runs unbroken from the circumnuclear ring to the farthest, faintest curl at the tip of each tidal feather. Numerical experiments reproduce the Condor galaxy by launching a low-inclination, prograde flyby of a smaller companion with a mass ratio of roughly 1 to 10, n-body particles stand in for the old stellar disk while smooth particle hydrodynamics tracks gas, cooling, and feedback. When the intruder crosses the disk, the model spins up a strong bar, sends m equals 2 density waves outward, and draws out 2 vast tidal plumes whose curvature and length match what telescopes see. Tune the pericenter to tens of kiloparsecs and you also recover the observed m equals 1 lopsidedness, an off-center light distribution that decays only slowly in a deep, roundish halo. The same runs predict that material flung to apocenter will rain back on timescales of a few 100 million years, thickening the outskirts and keeping the winged superspiral supplied with low-level star formation long after the main shock. To read that history from light, observers map ages and motions simultaneously. Integral field spectroscopy lays down velocity fields with S-shaped isovelocity contours that betray non-circular streaming along the bar. At the same time, H-alpha and far ultraviolet trace young clusters that line up at curvature changes like punctuation marks on a sentence. Where the gas surface density is modest but mid-plane pressure peaks, bar ends, arm bends, CO lights up, demonstrating that a pressure-regulated recipe for star formation outperforms a simple surface density threshold in the far wings of the Pavo Titan. Depletion times go long in those plumes, yet the few massive, hinge clumps that do ignite serve as crisp clocks whose line ratios timestamp the passage of the perturbation to within tens of millions of years. The avian megaspiral also stress tests how disks mix their metals. Abundance gradients flatten after the encounter because enriched gas rides the plumes outward while bar torques pull slightly more metal-rich material inward, fountains seed the halo, and reaccretion returns that gas pre-enriched, blurring any sharp steps that would have recorded strictly inside-out growth. Tidal dwarf candidates at tail tips inherit high metallicities for their small masses, a telltale that they condensed from disk debris rather than pristine, dark matter-dominated mini-halos. Kinematic self-binding tests, velocity dispersion versus size, separate bound dwarfs from ephemeral knots, letting the feathered colossus act as a laboratory for dwarf galaxy formation in the present day. Magnetism sketches the invisible scaffolding. Polarized radio continuum aligns along concave arm edges and the offset dust lanes of the bar, implying field stretched by shear and compressed by shocks. That ordered field adds magnetic pressure that raises the effective gene's length in the thinnest plumes, subtly suppressing overfragmentation. Relativistic electrons from young supernova remnants backlight the pattern, so radio maps place a near real-time stencil of recent star formation over the slower fading stellar light of the sky-wide spiral. Together with turbulence measurements from line widths, these data let plasma physics share the stage with gravity in setting when and where gas condenses. Vertical structure remembers the encounter long after the arms relax. Bending waves ripple through the outer disk of the Raptor spiral, their amplitude with radius bracketing the disk-to-halo mass ratio, warped HI layers and returning streams cross the plane at angles, puffing a proto-thick disk and seeding faint UV knots beyond the canonical optical edge. Because damping is slow and a massive, gently rising halo, these corrugations persist for several rotation periods, a low-contrast echo of the flyby written in the galaxy's z-direction. The survival of 500,000 light-year wings under that gentle rotation curve explains how the Condor-scale disk can look torn and yet remain dynamically coherent. At the core, orbit families pace the heartbeat. Gas on X1 orbit streams into straight, offset lanes where shocks form. If inner Lindblad resonances allow X2 orbits, inflow stalls into a circumnuclear ring whose H2 knots light up in bursts. Feedback from clustered supernovae briefly raises the local tumor Q, throttling the very inflow that fed the burst, a self-regulated loop that flickers rather than roars. Over hundreds of millions of years the bar in the bar-forged Titan transfers angular momentum to the outer disk and halo, slows, migrates corotation outward, and eventually buckles into a box/peanut bulge, subtly moving where rings gather and where spirals launch. Comparative anatomy clarifies the niche. Ultra-diffuse Malin-class giants achieve scale with symmetry and low surface brightness. UGC 2885 is massive yet orderly. By contrast, this peacock behemoth couples extreme size to unmistakable tidal sculpting, flared plumes, off-center light, patchy outer star formation, while still running a competent bar engine in its core. That compression of phenomena, inflow, feedback, migration, mixing, reaccretion, into one nearby system turns the galactic Condor into a benchmark, match its pitch angles, torque phase shifts, metallicity maps, polarization patterns, and S-twisted velocity fields in one simulation, and the physics is likely right. Environment keeps the story going. In a modest group, repeated but gentle perturbations are more common than single, catastrophic hits. Each pass nudges the pattern speed, restirs the outskirts, and occasionally reprimes the center without shredding the disk. If the present companion is captured, dynamical friction will spiral it inward and reflare the wings, surging inflow and hastening bar buckling. If it escapes after trading momentum, the plumes will relax over a few rotation periods while returning gas keeps the ultra-extended spiral speckled with low-efficiency star formation. Either branch preserves the core lesson, gravity sculpts the stage, gas negotiates the terms, and stars take notes from nucleus to farthest feather. Because the interacting megadisk sits close enough for clump-scale resolution yet acts as a local echo of gas-rich giants at cosmic noon, it bridges epochs for theory. Observers can demand that a single model span from parsec-scale cloud physics to 100 kiloparsec tides, reproducing not just morphology but age gradients, line widths, magnetic alignments, and rotation curve subtleties. When those constraints are met together, confidence grows that the same grammar, non-axisymmetric torques, turbulence, magnetic support, feedback, and a cushioning dark halo, governs less flamboyant spirals as they quietly rewrite themselves across the nearby universe. In that sense the winged giant is both spectacle and standard, a readable long sentence in which gravity writes, gas edits, and stars file the minutes for anyone with a telescope to read. Even timekeeping inside the feathered colossus can be done multiple ways, and they agree within uncertainties. Dynamical clocks, orbital periods inferred from rotation curves, tick at a few 100 million years in the mid-disk and lengthen toward the tips of the plumes. Stellar clocks, age gradients along the beads on a string, read from H-alpha, FUV, and optical colors give the same sequencing, compression first at bar ends, then at arm bends, then far out along each tidal feather. Where the bar meets its corotation radius, star formation pauses into dusty crescents as gas piles at resonances. Slightly farther out, where shear slackens and shocks intersect, the raptor spiral lights hinge clumps that become the loudest punctuation in its recent story. Because dust veils the core, panchromatic fitting matters. Spectral energy distribution models that combine ultraviolet through far-infrared fluxes disentangle the age, dust degeneracy for young clusters and recover realistic attenuation laws that vary across the sky-wide spiral. Steeper, SMC-like curves appear in harshly irradiated shock fronts. Grayer, starburst-like attenuation emerges where birth clouds dominate. Those curves, paired with CO-based gas masses and HI maps, let astronomers close the baryon budget from atomic halos to molecular clouds to newborn stars, and, with mid-IR PAH diagnostics, identify where shocks or hard UV fields have shattered the smallest grains after the flyby. The circumgalactic medium around the interacting megadisk is not dead space but an active ledger. Neutral streams traced in 21 cm emission arc beyond the optical body, while a hotter, X-ray, thin component hints at weak shocks where returning gas re-enters the plane. If a background quasar or bright galaxy sits just behind one wing, absorption line spectroscopy can read metal columns and ionization states directly, testing whether the returning rain is already enriched by earlier starbursts. A metal-rich halo that feeds back onto the disk would explain why abundance gradients in the winged superdisk are so flat compared with unperturbed spirals. On the dynamic side, the bar-forged Titan is a clean laboratory for separating torques from tides. Harmonic decompositions of velocity fields distinguish m equals 2 bar streaming from global m equals 1 lopsidedness, while phase offsets between gas lanes and the stellar bar measure the sign and strength of angular momentum transfer. Where the gas leads the bar, it is losing angular momentum and sliding inward. Where it trails, feedback has temporarily stiffened the local disk. Stitch those offsets azimuthally and you get a torque map, gravity's push rendered as a function of angle, showing exactly how the Pavo Titan fuels its center without erasing its disk. Turbulence and magnetic fields shape the fine print in the Condor scale disk. Power spectra of gas emission approach Kolmogorov-like slopes across kiloparsec ranges, implying a cascade from supernova-driven superbubbles down to cloud-scale shocks. Polarized radio continuum shows fields aligned along concave arm edges and straightened in bar lanes, a topology that both channels inflow and raises the effective gene's length in the thinnest plumes. The result is patchy, regulated star formation, efficient where pressure peaks at resonances, throttled where magnetic tension and shear grow, a balance that keeps the far wings spangled but not saturated. Cluster demographics extend the archaeology. The initial mass function of young clusters in the avian Leviathan looks like a power law with a high mass cutoff that shifts upward in the most compressed zones, consistent with higher midplane pressures at bar ends and arm bends. Infant mortality rates, rapid early dissolution for loosely bound associations, are higher in the outer plumes, where tidal stresses and low ambient pressure work against survival. The few that are born dense may endure and, over a Hubble time, fatten the system's globular cluster census with members whose chemical fingerprints still betray birth in a once-stressed wing. Even the vertical dimension holds memory. Bending waves and corrugations ripple through the outskirts of the ultra-extended spiral, their amplitudes bracketing the disk-to-halo mass ratio. Warped HI layers imply a deep, roundish halo that gently rises with radius, exactly the cushion needed to keep 500,000 light-year wings coherent over many rotation periods. Where returning streams cross the plane at an angle, they thicken the outskirts and plant faint UV knots beyond the classical edge, so the peacock giant writes a long afterword in low surface brightness light long after the main act of the flyby has faded. Placed among its peers, the galactic Condor is the rare system that compresses many chapters of disk evolution into one readable paragraph. Encounter-seeded spirals, fast bar inflow, feedback-regulated bursts, metal mixing, magnetic guidance, reaccretion-grown outskirts, and slow secular thickening. That is why simulators love it, a single target that forces a model to get the morphology, the torque phases, the age gradients, the polarization patterns, and the S-twisted velocity field right all at once. When a run nails those constraints together, confidence grows that the same quiet physics, non-axisymmetric torques, turbulence, magnetic support, feedback, and a cushioning dark halo, governs the less theatrical disks filling the local universe. And until the companion either spirals in or sails away for good, the wingspan colossus will keep revising its script, gravity drafting the plot, gas negotiating the dialogue, and stars recording every scene from the circumnuclear ring to the farthest curl of each tidal feather. In the wingspan Titan, quenching and reignition operate like alternating seasons. As the bar strengthens and thickens, dynamical heating and rising shear boost the effective stability of the inner disk, morphological quenching the quiet star formation without exhausting fuel, yet the outskirts keep catching returning streams, where oblique impacts lower shear and briefly push midplane pressure over the atomic-to-molecular threshold. That is why the Condor scale spiral can show a calm, dust-rich core at the same time its tidal feathers sparkle with young associations, stability at the center, opportunistic ignition at the edge. Feedback sculpts the details with a surprisingly light touch. Clustered supernovae drill chimneys that couple weakly to such a deep potential, hot gas vents, cools, and rains back as a metal-rich drizzle, enriching the circumgalactic medium and flattening radial abundances when it re-enters the plane. In the Peacock Giant, this fountain cycle writes a slow chemical palimpsest over the sharper gradients that inside-out growth would otherwise leave, so spectroscopic maps read like notes scribbled atop an older script. The Raptor megaspiral also turns out to be a precise laboratory for resonance cartography. Bar pattern speed places corotation just beyond the bar tips, while inner Lindblad resonances host a fickle circumnuclear ring that flickers on feedback timescales. Farther out, an outer resonance collects gas into a broken suturing where spiral segments stitch together. Because the disk is so overscaled, small secular drifts in pattern speed shift these resonances by tens of kiloparsecs, relocating star-forming crescents the way a tide line marches up a beach, slowly, relentlessly, and legibly. Star cluster archaeology keeps time on top of that map. Luminosity functions in hinge clumps tilt bright where compression is strongest, infant mortality rises in the far wings where ambient pressure is low. The survivors near bar ends, born dense under high pressure, are the best candidates to age into genuine globulars. Decades from now, when those clusters have faded into red embers, the feathered colossus will still carry their chemical fingerprints, a fossil record of bar-driven weather written into the halo of ancient jewels. The sky-wide spiral even lets theory separate which knobs matter most. Vary the halo's roundness in simulations and the vast wings either press S away or hold their pose, dial up gas fraction and the bar overfeeds the center, triggering a short, hot starburst followed by a longer lull, strengthen magnetic fields and fragmentation in the thinnest plume softens, changing beat spacing along the strings. Matching all of those observables at once, pitch angles, S-twisted velocity contours, polarization ridges, abundance gradients, age sequences, forces models to honor the same compromises gravity struck in the real system. Dynamical friction sets the branching future. If the companion's orbit decays, the bar-forged Titan will see its wings reflare, its inflow surge, and its bar buckle into a box/peanut bulge before the pair coalesce into a thicker, earlier type remnant. If the intruder escapes after trading momentum, the plumes will relax over a few rotation periods, returning streams will continue to seed slow star formation in the outskirts, and the center will hum along in self-regulated pulses. Either way, the galactic condor remains an anthology in motion, gravity writing, gas editing, stars archiving, across a page more than 500,000 light-years wide. The cosmic condor also pressure tests how angular momentum budgets govern size. Specific stellar angular momentum J \J_J \J inferred from rotation curves and light profiles lands this system on the extreme, high J \J_J edge for its mass, explaining why modest tidal torques can fling material to radii where most spirals simply run out of stable orbits. That same surplus of ordered motion lets the outer disk remain surprisingly cold after the flyby, so the Peacock Giant keeps its feathers coherent instead of phase mixing into a featureless smear. In phase space, you would see narrow ridges of nearly circular orbits interleaved with streams nudged by the companion, a kinematic palimpsest that decays only as dynamical friction and weak scattering slowly thicken the sheet. Fuel supply in the winged Leviathan is a two-loop economy rather than an open pipeline. A galactic fountain lifts metal-rich gas via clustered supernovae, cools it in the halo, and rains it back onto the outskirts, while tidal fallback returns loosely bound streams on elongated orbits. Fresh, low metallicity inflow from the larger-scale web plays a smaller, steadier role. The mixture explains why the far plumes host near-solar H2 abundances for their low surface densities. Most of that gas was born in the disk, not captured pristine. Combine those abundances with dust-to-gas ratios and you can estimate how many fountain cycles the Raptor spiral has already run, a chemical clock that ticks between bursts. Stellar populations across the feathered colossus encode dynamical weather in their kinematics. Age-velocity dispersion relations steepen where the flyby punched bending waves through the sheet. Younger clusters in the plume stay cool and ordered, while intermediate-age stars near the bar ends show extra radial heat from repeated shock passages. Circularity distributions, how closely orbits hug perfect rotation, split by age reveal migration without heating near corotation and true heating where the bar and companion acted in concert. From that forensic mix, modelers back out when the bar strengthened, when hinge clumps peaked, and how quickly the outer wings began to relax. Even without a glaring nucleus, the bar-forged Titan lets astronomers time the inner engine. Gas following X1 orbits into offset dust lanes shocks and cools. If X2 families exist inside an inner Lindblad resonance, a circumnuclear ring traps inflow until feedback spikes turbulence and the local tumor QQQ, stalling the conveyor. Radio recombination lines and fine structure mid-IR diagnostic separate compact, very young H2 pockets from slightly older clusters still swathed in warm dust, so the heartbeat of the center can be read as a sequence of short bursts separated by feedback length lulls. Flicker, don't blaze, exactly the mode expected when a massive bar feeds a black hole by intermittent sips. Magnetic topology in the sky-wide spiral adds invisible rails to the traffic plan. Polarized continuum aligns along concave arm edges and straightens into the bar lanes, showing field stretched by shear and compressed by shocks. The added magnetic pressure lifts the effective gene's length in the thinnest plumes, so fragmentation arrives as widely spaced beads on a string, rather than a foamy spray. Farther in, field-guided flows help collimate inflow toward the ring, while turbulent diffusion stirred by clustered supernovae slowly randomizes orientation between bursts, a cycle you can watch by comparing polarization maps to the evolving pattern of young clusters. Environment keeps nudging the script. The Pavo Titan lives in a modest group where repeated, slow perturbations are more likely than one catastrophic hit. Each passage from a neighbor tweaks the bar's pattern speed by a few percent, sliding corotation and resonance rings by tens of kiloparsecs on secular timescales. Because the disk is so overscaled, those small shifts relocate preferred star-forming crescents like a tide line inching up a beach. If the present companion is captured, the wings will briefly reflare, inflow will surge, and the bar will likely buckle into a box/peanut bulge. If the intruder escapes, the plumes will relax over a few rotation periods while returning streams keep the outskirts lit with low-efficiency star formation. Comparisons sharpen why the interacting megadisk matters. Malin-class giants achieve scale with ultra-diffuse symmetry and low star formation efficiency. UGC 2885 is massive yet orderly. Here, extreme size couples to unmistakable tidal sculpting, offset light, M equals 1 lopsidedness, patchy outer nurseries, and still runs a competent bar engine. That compression of processes into one nearby target lets a single simulation be judged on many axes at once: pitch angles and torque phase shifts, age gradients and polarization ridges, metallicity maps and S-twisted velocity fields. When a model clears all of those bars together, confidence grows that the same grammar, non-axisymmetric torques, turbulence, magnetic support, feedback, and a cushioning dark halo, governs quieter disks, too. Looking further ahead, the Condor scale spiral is destined to edit itself by slow grammar changes rather than a new chapter title. Bars tend to slow and strengthen as they torque the outer disk and halo, corotation drifts outward, resonance rings migrate, and vertical instabilities eventually buckle the bar. Outskirts fed by reaccretion thicken into a faint, metal-rich envelope. Some tidal dwarf candidates detach as satellites, others dissolve and rain back. Whether or not the current partner returns, the lesson that the galactic condor keeps riding from nucleus to farthest feather stays the same. Gravity drafts the plot, gas negotiates the dialogue, and stars file the minutes in light, line by line, across a canvas more than 500,000 light-years wide.